Good morning, good afternoon, or good evening, folks. Welcome back to Unit 7, which is all about motion. Yesterday we covered Lesson 7.1, Scalar Quantities. Today we're going to move into Lesson 7.2. This lesson is called Vector Quantities, Displacement, Velocity, and Momentum. It might help you to go back and review what we talked about yesterday in Lesson 1. I'll be referring to some of those things today as we go through Lesson 7.2. So let's start off with the definition of a vector quantity. What is a vector quantity? Well, if you remember, a scalar quantity is any measurement where the direction doesn't matter, like speed, distance, and time. We don't care what direction you're moving in when you tell us the distance that you traveled, just the number is important and the units. With a vector, the direction does matter. So you can think of a vector as like a scalar, but the direction is important this time. Some examples of vectors include displacement, velocity, and momentum. We'll talk about some other vectors in upcoming units like force. I showed you yesterday this animation of three cats that were moving along this grid. We're going to look at this animation again, but this time we're going to pay attention to what direction they wind up in. So it's the same three cats doing the same three movements from yesterday, but this time I've added in some arrows to show the direction from where they started to where they ended up. So all cats still traveled a distance of 6 squares total, but this cat winds up a 4.47 squares away from his starting point, and not straight down or straight to the right, but kind of in between. This cat winds up only 2 squares away from where he started. This cat winds up about 3.16 squares to the left and a little bit down. So we say that these are the cat's displacements, okay? Because it matters not only how far the cat's traveled, but also in which direction the cat wound up versus where it started. Now there are many different ways that we can define directions. I'm not going to go over all of these. You can pause the video and read them if you'd like. But some of the most important is to use compass headings or signs. We will often define a direction as being positive or negative. If we're just moving forward and backward, that's a perfectly good thing to do because it's easy and we can all agree that one direction is positive and the other direction is negative. So let's start with the concept of displacement. Displacement, as you can see here, is the difference between an object's final position and its original position. Its abbreviation is delta D. You read that triangle as delta. Whenever you see delta in science, it means that something is changing. So it's the change or the difference between where an object ends up and where it started. If you go online looking for some extra help, you may see somebody indicate that the displacement is delta x, and that's fine too. They just mean something is moving along an x-axis, and the delta x is how far it travels along that x-axis. So delta x and delta d can both be symbols for displacement. I have here 4 colored circles or 4 colored balls that are going to move along this track, and we're going to talk about the distance that they travel and the displacement. And pay attention to this compass rose over here. So if the colored ball moves to the left, and that's going to be west, and if it moves to the right, then we're going to call that east. So let's start off with the red one. The red one starts by moving 3 squares, and each square is 1 meter long, in this direction. So its distance is 3 meters, but its displacement is 3 meters east. We have to indicate the direction if we want to make it a displacement. Now the yellow one, it moves 2 meters to the west. So the distance traveled is 2 meters and the displacement is 2 meters west. Now the green one starts by moving 3 meters to the east, but then turns around and moves 2 meters to the west. So the total distance traveled is 5 meters. Remember, distance doesn't care about direction. It doesn't matter that it turned around. The displacement is 1 meter to the east because once the ball stops moving, it is exactly 1 meter to the east of where it started. So that's the difference between distance and displacement. Distance doesn't care about direction, displacement does. The blue one starts by moving 2 meters to the west and then turns around and moves 2 meters to the east. So the total distance traveled is 4 meters. but the displacement is 0 meters because it wound up exactly where it started. So it's like if you run a race around a circular track or an oval-shaped track, the distance will be the length around that track. You might run, 500 meters or however long it is to go around that track. But your displacement will be 0 because you will end the race exactly where you started it. Now that we understand displacement, let's talk about velocity. A lot of people confuse velocity with speed, and they use the two terms as if they mean the same thing, but they don't. Velocity is a vector, which means it has a direction. Speed is a scalar, which means it does not have a direction. So when we calculate velocity, instead of saying distance divided by time, we say displacement divided by time. V is equal to delta d divided by t. And just like with speed, we can draw a triangle for the velocity formula. Velocity is equal to delta d divided by t. If we wish to solve for displacement, we can multiply velocity times time. Delta d is equal to v times t. And if we wish to solve for time, we can divide displacement by velocity. T is equal to delta d divided by v. Again, 3 formulas for the price of 1. Moving right along. So let's do some word problems with velocity. A cat walks 50 meters north, so we have a distance and a direction, so that makes it a displacement in 20 seconds. What is the cat's velocity? So the given information, the delta d is 50 meters north, and the t is 20 seconds. Unknown is the velocity, so v equals question mark. I need an equation that will give me the velocity when I know the displacement and the time. V is equal to delta d divided by t. Next I will substitute, so I'll replace the delta d on top with 50 meters north. And it is important that you keep that direction because the direction is going to become part of the velocity. The t, I'll replace that with 20 seconds. Next I grab my calculator and I solve. So 50 divided by 20 is 2.5. The unit is going to be meters divided by seconds, or meters per second, and the direction is north. If you don't put north, then you've just given me the speed, not the velocity. You have to have the direction in order to make it velocity. Does this answer make sense? Well, yes, it does. We were trying to solve for velocity. Meters per second is a unit for velocity, and the direction means that it is a vector quantity and not a scalar. A truck drives 25 meters per second east. What is the truck's displacement at the end of 60 seconds? So listing what we know that the truck's velocity is 25 meters per second in the eastward direction. We know that's a velocity because meters per second is a unit for speed or velocity, and the direction makes it a velocity. The time is 60 seconds. We are trying to solve for the truck's displacement. And displacement will be equal to velocity multiplied by time. Delta d is equal to v times t. Substituting, v is 25 meters per second east, and t is 60 seconds. You grab your trusty calculator and multiply 25 times 60. The calculator will tell you that the answer is 1,500. Now let's talk about this unit, meters east. Well, meters per second times second. We've got seconds on the bottom here, and we have seconds on top here, so they're going to cancel each other out, and we're going to be left with just meters for our unit, and the direction is going to be the same as the direction of the velocity, so east. Does this make sense? Yes. We're solving for displacement. We got meters. Meters can be used to measure displacement along with the direction, so this works. A helium balloon rises at a rate of positive 4 meters per second. So we're using positive as the direction here to indicate upward. How long does it take the balloon to have a displacement of positive 1,300 meters? All right, so we're being told that the velocity of the helium balloon is positive 4 meters per second. Include that positive sign. I know in your math class you may have been told that if it's positive you don't have to put the positive sign, but in this case it does indicate a direction. And the delta d, the displacement, is positive 1,300 meters. What are we trying to solve for? Well, the question says how long, so we're trying to solve for time. I need an equation for time when I know velocity and displacement. So t is equal to delta d divided by v. Very important to become familiar with this triangle so you don't accidentally put something like t is equal to v divided by delta d, and then you would get the wrong answer. Substituting, the delta D, the displacement, is positive 1,300 meters, so we put that on top. And the velocity is positive 4 meters per second, so we put that on the bottom. And then we grab our calculator and we divide. 1,300 divided by 4 gives us 325. The direction doesn't matter because time is a scalar quantity, so the positives will, we can just sort of remove those. And then for the unit, we have meters on top and meters on the bottom, so they will cancel out. And then we have seconds on the bottom, but it's on the bottom of the larger fraction, so it kind of flips up to the top. Time is equal to 325 seconds. Does that make sense? Yes. We are measuring for time. We wound up with seconds, so that looks pretty reasonable. There is one last vector quantity that we need, that we need to talk about before we wrap up this lesson, and that is momentum. Momentum is kind of hard to define, but we say it's a quantity of motion of a moving object. Another way I like to describe it is to say that momentum is how bad it would be to get hit by something that's moving. If something has a lot of momentum and it hits you, then it's going to hurt a lot more than something that has only a little bit of momentum. So you can kind of think of it as in terms of, when I want this object to hit me, well, if I can calculate its momentum, I can determine how bad that would be if it did. Now, for reasons that I can't explain, the abbreviation for momentum is a lowercase p. Yes, I'm aware there is no letter P in momentum. We just have to go with this. And the unit for momentum is pretty confusing. It's kilograms times meters per second. And the reason that that's the unit for momentum, it has to do with the formula for momentum, which we'll look at in just a moment. Momentum is a vector, which means it does have a direction. So when you calculate the momentum, you have to include that direction. The general formula for momentum is equal to mass times velocity. So that's why we get kilograms times meters per second. Kilogram is a unit of mass. Meters per second is a unit of velocity. When we draw a triangle for momentum, we can put the P on top, and M times V have to go on the bottom because they get multiplied to give momentum. If we wish to solve for mass, mass is equal to momentum divided by velocity, or P over V. And if we wish to solve for velocity, velocity is equal to momentum divided by mass, or P over M. I know it can get very confusing because we're talking about momentum and mass is M and momentum is P. But again, you just have to kind of get used to it, and that's just how we're going to use those symbols. Now, this is important to remember that an object that is not moving has zero momentum. It doesn't matter how big it is. So if we compare this 18-wheeler to this tiny little butterfly that is flying at just 0.5 meters per second, it might seem like for sure the 18-wheeler would have more momentum because it's huge, but it's not moving, so the momentum of the 18-wheeler is zero. And even though the butterfly's momentum is tiny, it's still bigger than zero. So as long as this butterfly is moving and the 18-wheeler isn't moving, then the butterfly has more momentum. Now, if the 18-wheeler starts moving at the same speed as the butterfly, then yes, of course, the 18-wheeler would have loads more momentum than the butterfly. Okay, but as long as the 18-wheeler is sitting still, it has zero momentum. So let's do a word problem with momentum. A dog with a mass of 15 kilograms is walking at a constant velocity of 2 meters per second southwest. What is the dog's momentum? So let's list the information that we've been given. The mass of the dog is 15 kilograms, and the dog's velocity is 2 meters per second southwest. I just abbreviated here, southwest SW. What is unknown is the momentum, P. So we need an equation that will solve for momentum when we know the mass and velocity. P is equal to M times V. We substitute in the information that we know. So for mass, we replace that with 15 kilograms, and for V, velocity, we replace that with 2 meters per second southwest. And then you grab your calculator, or perhaps you can do this calculation in your head. 15 times 2, the answer is 30 kilograms times meters per second southwest. So yeah, that's a big, bulky unit, but that is the unit for momentum, and that is the direction because momentum is a vector. All right, so that's going to wrap it up for lesson 7.2. As always, I will upload an assignment in Google Classroom, a very short assignment of 4 or 5 questions. If you would please take a moment to do those questions and then submit that to me, I will try to offer feedback. Again, I appreciate your attention. Now, tomorrow we're going to go into our next lesson, which is all about acceleration. So we'll be talking about things that speed up or slow down or change their direction, acceleration being a change in velocity. Thanks for your attention. Take care, stay safe, and keep washing your hands. Talk to you later. Bye.